to give them an alternative measure of distance, which should give you back exactly the same thing. And I told you that if you this leads to sort of two separate measurements of the value of the expansion rate of the universe, or the Hubble parameter today. There's the one that you get by, if you want, using the hydrogen atom as a physical system, which allows you to essentially determine the physics of recombination, and using the temperature of the CMB to understand how far away at what redshift this happened. And if you assume that the universe up to recombination was basically completely standard, and then if you assume that from the moment of recombination to today you have lambda CDM, you end up with this value, this low value of this Hubble parameter. But remember, this is implied, right? Remember, this Hubble parameter is it's not really a measured quantity. It's a derived quantity from the observations of the CMB and assumptions of certain models. And there's the local value of H0, which is derived from building a ladder of distances, looking at parallax, Cepheid variables, etc., and supernovae close by, obtaining the real luminosities in this way, because you can really measure the distance to very, very close ones, and then extending this a little bit further out, so you can capture the cosmological distances, cosmological redshifts and flow, which leads you to this ever more precise value of H0. And there's a huge amount of debate as to which one is correct, right? And sort of this thing is essentially right now the biggest controversy in cosmology, I'd say. The question is, the big question is this real, right? I showed this a little bit yesterday, that this is a trend that's kind of been around. So these are these values implied from the CMB measurements, and these are the values in yellow, which are implied by the local distance ladder measurements. And you can see they've been sort of diverging consistently throughout. Errors were very big in the past, so no one saw this, but it's not like it's just appeared recently. One thing to stress, though, is that if you, okay, let me show you this plot. So what this plot is, it's from DES, which is a survey which is mainly focused on weak lensing. So it's they're measuring the shapes of galaxies to try to ascertain the strength of the gravitational field. But one of the things that they do, because they're really doing a very, very wide survey, is that they see supernovae sometimes. So what this appears to do is it's called the reverse distance ladder technique. What they do is they take which was the BAO? So the BAO data are the black squares. They take the BAO, they use the BAOs as an anchor for the supernovae. So they say, look, let's imagine that the distances, which, if you want, the distance is implied by BAOs, and which really come from this sound horizon distance, which is embedded inside the CMB. Those are correct, and then the question then is this compatible with the supernovae? And so they plot here the circles are the DES supernovae, and then there's some low redshift catalog of supernovae extending down to the redshift of 0.02, and you can see that roughly they see that these two distance measures are compatible. And the claim is, that it's compatible, so this is a plot of the distance, but over here you have the implied value of H0, and they find that, yes, it's compatible with this low Planck value. So you might say, look, so these guys have proven, they come down to very, very low redshifts, and they see very low H0. They're also using supernovae, so everything, so clearly this Planck value must be fine. But I just want to stress that you really only have one distance. Right? So both supernovae and the BAOs measuring, okay, one's angular, one's luminosity, but there's this dual relationship to do with the redshift, so you can just translate one to the other. There's an exact relationship, and they have to be compatible, right? So the question is, under what circumstance would you have ever been able to say that there's some different value of H0 which you've arrived at by doing this combination of data? You know, and the answer is that there isn't one, because you're, you know, all you're doing is you sort of, the problem that we essentially have is we don't know what H0 is. So one way of working out what H0 is by setting the value of the sound horizon. It's some arbitrary normalization for these points. And then there's a separate data set, which is this you know, these data for the supernovae here, which again, we don't really know what the overall normalization of this is, but you're putting the two together and you're just picking one normalization or another one. So if you use the BAO normalization, you will just get back exactly what you would have got from the BAOs, unless there's some incompatibility between the distances, but it cannot be by definition because it's just already measuring the same. So you see, if you found that there was some other value here that this gives you, I think this would have told you that there's some fundamental problem with supernovae, in that, but not that the distances they measure are different, but that they're kind of evolving in time or something like that, and they're not really standard candles. So these sort of analysis, I mean, you know, to me at least, are not particularly convincing that they've resolved anything. So the question is, you know, what else can you do? And the answer to this, finally, is that you should just use something that is just a completely different method, and gravitational waves provide that. Yeah. Let me remember. So there's some uncertainty to do with you know, your lack of knowledge for the sound horizon, what this is. So you don't really know what the distances are if you don't know what the sound horizon is. So they're essentially using some sound horizon that's implied by the BAOs, but they don't really. So that's something to do with this. So your uncertainty in H at any time is kind of inside this. So these are not two colors. I think this is just some overlap. So I think this will be like a 1 sigma, and I think this is a 1 sigma of what they're fitting, and this is the fiducial one that's sort of everyone that you get out of Planck. So this is the Planck one, and this is the Planck 1 sigma, or maybe 2 sigma, I don't know. And this is the equivalent of what they're getting with the new data. So you know, the point is they overlap, and therefore they're compatible. Any other question? Okay. So what I'll talk about is a bit about gravitational waves, and we've all been approaching this from different directions, and none of us, apart from Ricardo yesterday, have given you the formulae for this. So and I don't want to be the ones to be deriving them. So I will just quote some formulae which you'll get in Mario's course, I guess. Let me first tell you about how you can use gravitational waves in cosmology and why you can use them. So remember that the reason why you could say something, you could make plots like this. So you know, distance versus redshift, or you know, H0 is a derivative of distance, right? So distance versus redshift is because you have this, you have these null geodesics on which light propagates, and they have some, and the matter and the universe have some focusing properties for these light geodesics. So it turns out that the story of gravitational waves is exactly the same. So you know, there's some generation mechanism which is understood very well, but from my perspective, it's kind of you know, it's just like the generation mechanism in supernovae. We understand something better or worse. There's some source, and then they propagate to us. Okay? And the point of what I'll show in a moment, they propagate in exactly the same way as light does. So you get exactly the same sort of physics, in principle, out of them. So let me do a little bit of remember, I derived this geometric optics approximation to electromagnetism. So I'm going to do the same thing from gravitational wave physics now. So the way to think about this is that there's some metric which consists of some background, and there's some fluctuation which is small, h mu nu. And for me, so you know, in most of what's when Mario will be talking about this, he'll presumably be taking this to be flat space-time, because sort of roughly you don't care about cosmological expansion. But for me, the fact that this is not flat is important, because I'm talking about cosmology. So there's some cosmological metric g bar, and there are small fluctuations around that, which I will treat as linear. So let's say there's some small parameter epsilon here. And then I just take Einstein equations. And write and expand them to first order in this h mu nu around some arbitrary background g mu nu bar. And you get, actually, sorry, let me not call it bar, let me call this hat. So again, you get sort of a box operator nu to h mu nu bar. As h mu nu bar is just trace reversed h mu nu. So you define it to be h mu nu minus the trace of h mu nu. Where this trace here you do with the background metric. Sorry, this was hat. So you get this guy. Okay, so this is what the wave. This is a wave operator, and therefore this is a wave, right? But you get corrections because these equations are nonlinear, right? So you get a correction to do with curvature, which looks like the Riemann tensor with some index structure, and this h alpha b bar, and then you get a term which I will define in a moment, which we'll get rid of by basically picking a gauge. So this is partially why I did the previous calculation for photons in this not gauge invariant way. It's again because it's most similar to the way that this works out. So Z alpha, and these hats all over the place appears because I'm forming these covariant derivatives, the curvature with this background metric. Okay, so they're sort of background quantities. And this is equal to some source, right? So if you want 16 pi g Newton T mu nu, that source and also contains higher order terms in H. But, I won't worry about them because I only care about the propagation, so I only care about the linear part of this. So this Z that I have here, I've defined it to be, again, the hat derivative of H. And remember that this H has symmetries, right? It's variant under diffeomorphisms. So I can make a transformation so if H goes to plus the symmetrized derivative of some vector psi, this is just a change of coordinates linearized, right? Then everything remains invariant. So this is a property of the light. Oh, it's back. It's back. So by choosing a particular gauge, I can make this go away, right? So essentially, this thing is not there in this equation, as far as I'm. Again, there's always with these gauges is a bit of a question sometimes of whether it's in vacuum, if it's not, but for my purposes, I can do this. Good. And I do the same thing I did before, right? I say that my h mu nu bar is the real part of some slowly varying amplitude. So unsurprisingly, since it's the box hitting this h mu nu, you get back the same expansion as before. You get minus omega squared k alpha h mu nu a. You get this term which you didn't like, which appears at first order. So I hit the oscillating part once with derivative, and the other one I leave for the non-oscillating parts. So I get plus d alpha k alpha of the amplitude times h mu nu. Oh, I didn't actually. Will again lead to this, thanks, which again lead to this flux conservation. And there's the term which is essentially the derivative hitting the h, which looks like k alpha d alpha h mu nu, also at order omega. So if everything is 0 at order omega, then I again get gravitational waves propagate null vectors. Because these guys are, if you remember, derivatives of scalars, I can commute the derivative when I hit this with derivative, and I get the statement that these null vectors are parallel propagated along null geodesics. So they remain null. This flux conservation again, and h mu nu gets parallel propagate along null geodesics again, which means that if if this was transverse here, it's going to be transverse on the other end. Yeah, exactly. So things are good. Yeah, so the Riemann term I throw away because what I care about, I'm doing an expansion in this omega parameter that I take to be big. So I'm taking the gravitational wave to have a higher frequency compared to the sort of typical cosmological distances that I care about here, right? So here, there's no derivatives. Derivatives are sitting, if you want, inside the R, hitting the background metric. There are no derivatives hitting the H. And therefore, the time variation, the fast time variation is only in the H. And since there are no derivatives hitting this, there's no contribution at either order omega squared or omega to this equation. This thing appears at order omega to the 0. But the omega to the 0 one is a complicated expression that essentially gives you back this equation again. So you might as well solve this if you want. Well, okay, but all the choices of coordinates that I can do are of this form, right? So this equation, in fact, is kind of coordinate invariant in some sense because they're all like that. No. I mean, and the Riemann tensor is invariant in this covariant, whatever, right? It's like you different components, but the physical meaning is fixed, right? It's a tensor. Yeah. So, yeah, H mu nu is not a tensor, so there's that issue, but I'm sure Mario will talk about that a bit. Okay, so the point of this is that whatever we've learned about what light does in cosmology or in any metric that you want to have, in the approximation in geometric optics is valid, which is the approximation that frequencies are much higher than the spatial variation of the background. The same thing will happen in gravitational waves. So, in particular, they will get redshifted. They will get focused by the curvature of the space-time, and therefore they will behave as if there's some luminosity distance or in principle angular diameter distance. The lensing effects. All these things will also affect gravitational waves because it's exactly the same equations, right? Because all the I'm really only making about physics, not really about there's a board there. Okay, so same. Let's call it propagation. Yeah. Propagation physics as light. So I'll talk a little bit about you can play around with this a little bit, and you can do some things which are very naughty to make the propagation physics of gravitational waves different, but that's now become very constrained. So in fact, one of the big achievements of LIGO has been to kill those ideas. So, good. Okay. So, so we have so let's try to do cosmology of gravitational waves. So there's some you can write down an expression. So roughly, so for photons, right, the way this worked is that you have some principle, there's some amplitude, and this amplitude falls as 1 over r, or flux, which is amplitude squared, falls as 1 over r squared. and this R was this very luminosity distance. That was the correct measure of how flux changes as a function of distance, right? So there's a similar sort of thing, because you have so you remember we're dealing with these double problems, right? That either you are looking at a single point source with light propagating out onto some detector surface like that, or you are dealing with with an extended source, and you're trying to measure the angle it subtends in the sky. So the setup of gravitational wave sources is this one. So there's an event which is located at a relatively small separation compared to the distances that we care about. So it's essentially a point source. It produces some amplitude. So there's a couple of holes merging, something like that. They produce an amplitude with gravitational waves. The local physics of the metric is extremely messy, but what comes out eventually in the radiative, as R goes to infinity in the radiative zone, exactly just this wave which is propagating, and its amplitude falls off as luminosity distance. So you produce two polarizations of the gravitational wave, and there's the amplitude. I'll write as this. So this is the amplitude. It's to do, there's a chirp mass. There's the phase. The amplitude is corrected by a derivative of the phase of the frequency here. And then there's some tensor here that appears as a result of the fact that your detector and the plane, the source, are in principle aligned in different directions. So n is the angle of sight toward the source, and L is the vector of the angular momentum of the inspiring objects. And you also get the cross polarization, which comes with a slightly different angular dependence. So I had a factor of 2 here in my notes. And then there's a different angular dependence here. Well, this should not like that. So you're receiving, in principle, some linear combination of these two, and detect them with this detector tensor Max was talking about. And so this is the amplitude, and it falls off as the luminosity distance. Okay, so this function f here, or phi, somebody will be showing all of this, right, Ricardo? So I mean, what f contains, that contains the chirp mass and mass ratios of all these things. Yeah, it's only the total mass. The f dot, so f dot contains the. Anyway, so the well, let me write this down. F dot is some function of the chirp mass times f mass ratio, and in principle, some parameters of the spins of the object. So in principle, if you look at the waveform, there's a template. You can find the various parameters of, this is what LIGO has done, right? You find the various parameters of by looking at the waveform, you find the various parameters of this sin spiral. You need to measure both polarizations, because if you do not, then you cannot resolve what you want to get for cosmology is the luminosity distance, but you can't resolve it because you don't know this factor unless you can really separate the polarizations. So that's one of the issues. So you really have to have good control of the amplitudes of the two polarizations separately. And in principle, well, great. You can essentially measure the luminosity distance. There's a problem though, which is that this expression is such that if I position so I can position an object at redshift equal to 0 with mass m1 and m2. So there's some binary system that's spiraling, and I'm locally in the universe, and I really see this m1, m2. I can rescale the masses. Let me make sure I get to be m1 times 1 plus z, and m2 1 plus z. So my mass ratios don't change, etc. My frequencies changes, of course, because my masses have increased now. But if I now position everything at redshift z equal to z, well, you know what I mean, at redshift z star. So I just move everything to a larger redshift. I rescale my masses. The prediction I get for this amplitude is exactly the same. Because if I have a source which is at redshift z, the frequency that I will observe will go down by a factor 1 plus z. And therefore, these combinations that enter this equation here, they're completely invariant. So there's a problem in using gravitational wave sources in cosmology that you don't, you can measure the luminosity distance very well. So you just have to see the thing, you have to decompose your two polarizations, so you get your angle, it's called the angle of inclination, right? You can get the luminosity distance. So this is if you want the opposite of what you get at supernovae, where you don't know the luminosity distance because there's some factor that you don't know. But here you don't know what the redshift is. Because you could just, so the event that you saw, in principle, could have occurred at higher redshift with bigger objects. And the signal you have received have been exactly the same. So the difference with gravitational wave cosmology is that, in principle, we're capable of getting luminosity distances very well, but we have to figure out how to get redshifts. And so it's a different problem to the problem of light. You're looking upset. No, so, but remember that what I want to do this plot, right? I would like to plot. What I would like to achieve is make some observations and measure two things for each observation. The redshift, I want to make my Hubble diagram. There's a redshift on here, on this axis. Compare them with some distance in this case. So in order to make my plot, for every event I have these two. I have to have these two. So I can get one, but not the other because it's completely invariant. So yeah, I can get luminosity distance in principle. Many of them, but I have to have some handle. And this becomes in some sense, a limiting factor for how well you can do. But, of course, if there's a will, there's a way. So the answer is not, look, we're going to see 1,000 events, and therefore we'll have 1,000 points on this plot. And therefore we'll do a superb job that's much better than anything the cosmologists have done because of this limit. So let me now tell you how you can try to go around this a little bit. And in fact, how LIGO has got around this. set everything here? Yeah. So clearly the way to do this, the most obvious way to do this, is that you want to also see not only this event in gravitational waves, but in light. If you can see it in light, then you can really measure the redshift of the light, because it's just atomic physics on some level, right? Exactly the same way you do things normally. So what that means is that it gets hard to do this with black hole mergers. But neutron-neutron star mergers, in fact, are what you want to do. But the price that you pay, of course, is that neutron stars, the masses are low, right? So you're only really likely to see them if they're close by. So for the purpose, from the point of view of LIGO, you're not really going to be able to build out a Hadot diagram of distances at large redshifts, because these, you don't see the signal from neutron stars is not powerful enough to we were showing that plot yesterday. You can see them up to 100 megaparsecs, which is about redshift of 0.2, maybe. So it gets into a significant distance into this plot, but it's not redshift of 1, 2, 3, which is of the what you might want to achieve. So with LIGO, you want to look at NS mergers, and you want to be able to see that so they have the counterparts. So, but the great thing about this, remember, let me write down the luminosity distance formula again. It's 1 plus z of the source integral dz by h of z. Okay, so you're only going to see these at very low distance, right? I mean, by cosmological standards, it's still 100 megaparsecs. So really, you're looking at something that is a low redshift event, but if you approximate this integral, you are sensitive to the value of h0. So in fact, LIGO provides a fantastic opportunity to, tell the cosmologist they're right or wrong. Because really you can extract this h0. So what do I have here? So in fact, this is what LIGO has done, right? So the question is this. So you can't do it for every event. So you have to localize it. You have to observe a counterpart, et cetera, et cetera. You have to be very lucky to get the polarizations correct, and it has to occur at a significant enough distance so that you are not sensitive just to the local dynamics of the local peculiar velocities, but you're sensitive to this cosmological expansion. So that means you really want to be going, tens of megaparsecs, 30, 40 megaparsecs away from us at least. So this is what it looks like right now. So the inclination angle is, not so this is from actually I didn't write, but this is GW 170817, right? The inclination angle is resolved only up to a certain precision, and this builds in a huge degeneracy in this constraint. So without constraining this very well, you don't know what the distance is. So there's this degenerate line exactly because you have these factors in the numerator and the denominator. So the two lines over here is exactly the controversy that we have. Planck versus, so this is not the latest. The latest is a little bit narrower, but essentially this is the Riess result from the local supernovae, and then this is Planck. And LIGO has put a constraint that looks like this. So the top line number currently is 74, but plus 16 minus 8. So, what's the hope that you'll do better? So the claim is that given this is going to be occurring, or is occurring frequently, you're going to have to be reasonably lucky to get the inclination in the right way. They have to be in the right place. But you, in principle, looking at, this is a page, this is the reference for this. You're looking at, of all the 40 events a year, and the moment that you get more observatories, you're beginning to resolve the position much better. So you're also much more likely to be able to find the counterpart, right? So there's a sort of improvement that you get as additional observatories switch on. Sorry, that's right, it's mean inclination, yes. So the claim is that, starting from, so by, in 3 years' time, you already would be looking at something of the order of, this is 3%, 3% measurement of H0. And in principle, you might be able to get to 1% or so by the middle of next decade. And of course, this 1% is a sort of similar precision that you get out of cosmology, and therefore will really allow you to discriminate between these two. Which one? Sorry, you mean the error bars here? It's some uncertainty. There's a number of events. Yeah, there's a number of events which will be of appropriate quality to be able to do some. Yeah, exactly. So neutron stellar measures which have parts that allows you to measure the redshift, and they're sort of at the right distance to be interesting. So if you're willing to wait around for other 5 years, this controversy will be over. There's let me tell you about one more thing, which is that so again, this is a projection of this uncertainty in H. It's quite non-Gaussian, right? The tail here is much bigger than the tail over here. And that depends on the actual inclination angle of the configuration. So the funny thing that happens is that depending on how you look at the event, you either have a tail which is very much extending into the high H0. This means the distances look lower. And you see there's this asymmetric error bars over here. But this is a completely random thing, right? So in principle, you also get inclinations which are either face on their edge on, and the error bars will be extending. This asymmetric will be this way. So this will be the long tail. This will be the short tail over here. And this actually allows you to. So this looks like a huge error bar, but in fact, because you'll be putting together. So you're putting together many measurements where the tail is either left or right. You should be able to, in fact, get after a few such measurements, actually a much better overall constraint than this naively suggests. So it's not. So this is, it's a non-Gaussian error, but it's the way its shape is event dependent. What do you mean the distribution? But I was then like, where they occur in the sky? So, yeah. So I don't know. So the statement is that you only care about the ones which are occurring, not very locally, but at some distance. So it's far enough away that you're not sensitive to the local peculiar velocities. But so this paper includes some formation. It includes some estimate of how really what the population is, where they happen to be, at what redshifts, their evolutions, etc. So I said this one. No, so this is the numbers here that generated. They include in some sense information about where you might be able to find them, right? But actually, so let me continue from this. So there's no alternative way of doing this. So, but there you really want to see a counterpart. You want to measure the counterpart's redshift, and you want to see the event and localize it in the sky, right? So and really measure the luminosity distance. But there's an alternative that you can do, which is statistical. So if you happen to know statistically where the sources happen to be, how they're distributed. So, given some particular range, the density of sources is this much. You can begin to use your knowledge of the population to try to guess at what redshift the source occurred. So this is so this blue line here is exactly an attempt to do that. Like, given that whatever our best understanding is of the distribution of binary neutron stars, the fact that we saw this event with some luminosity distance, we can try to constrain statistically the value of H0. Right, it's somewhere there. Yeah, exactly. Yeah, then somewhere else. Yeah, so this gives you a much wider base. But in principle, again, if enough, but you don't need. But the advantage of this, you don't need counterparts. So. So you have localization and some slice, and just everything that's behind that. But on the other hand, I guess you might imagine that given that the controversy of the H0 measurement today, one which is really based on measuring the actual redshift of the counterpart, is going to be much more likely to satisfy the doubters. Right. Again, it's just from this Chen paper. Yeah, so this is exactly. So this is that's why I put this in here. So exactly. So doing this sort of method, that the statistical method, you can see that in principle, as you get more, as you get more events, your error declines, but you're likely to reach 10%. Maybe is the estimate, rather than 1 to 2% from actually looking at the much smaller number of the events which have counterparts. But of course these are, who knows how many will be, right? things may happen more quickly or less quickly. So in principle, you might be able to, or you should be able to, if you just sit around for a few years, to figure out, this value of H0. So can you say more though? Because as I was telling you that you can measure luminosity distances. So with LIGO, not really, because you just don't have the sensitivity to such. But if you wait another 10 years, people are trying to decide how to build the space-based observatory for gravitational waves, LISA. And this is from there's a bunch of papers a couple of years ago where they discussed the science they might be able to do. So I just picked out a table to kind of give you an idea of what you might be able to do. So the claim is that you will be able to. It's looking at much lower frequencies. So in principle, you're able to see much larger objects. So the way you can do cosmology is that you can look at mergers of very large black holes that occur when galaxies merge. And it's really sort of not understood very well of really how many such events might occur, and how. So you can see that there are. So this first column here is roughly they say how many events they might be able to see over 5 years of this type. They're claiming that in principle it's you might be able to see them all the way up to redshift 8. So really you might be able to get luminosity distances for very, very, very large redshifts, and therefore build out this Hubble diagram that's even larger and continuously distributed if you want. With a single systematic probe from today to very large redshifts. So really sort of test the test this Hubble, the geometry of the universe in a very fine way. But we really don't know how many we might get, right? It's just an order of magnitude difference depending what you assume for the formation model. So right now, but here of course you're also in the situation where these black hole mergers, you have no idea really if, first you have to localize them, and again, this is exactly the same problem. So only some of them might be able to get localized to within 10 degrees that you're, let's say, realistically may be able to see with some sort of very wide field of view telescope that will be online around a similar amount of time. And then there's the question of whether you actually would expect them to have an electromagnetic counterpart or not. So you can see that rapidly the numbers. So each of the rows is you start with some particular formation model and some number of events that you think you might get, and these are the ones that you might actually be able to, so you have 680 events in principle that you might detect above some threshold, but only 70 of these you get localized, and then SST will actually likely to find one of them because it will not really have an optical counterpart. You're much more likely to see, on the other hand, some radio event, is the claim. So you're looking maybe at something like localizing most of these using the SKA and then following up with some, with another light telescope, because you still need to measure the redshift of this object. But you might end up with something of the order of 20 to 40 events over 5 years. That's their current estimate. And so it doesn't sound like very much. We're talking about thousands of supernovae right now, right? But nonetheless, so these are the Fisher matrices. So these are the current estimates of the errors that you might get on measuring these parameters if lambda CDM is the correct model and the fiducial values for these parameters that we have from Planck are the correct values, right? So you might be able to, depending exactly on which formation model that you have for the black holes, you might be able to do some, measure omega matter to, 3-4% if you're lucky over here, but more like 20% if you've got the wrong formation model. So right now it's kind of unclear as to whether you'll be able to do an extremely good job. But But then they're not powerful enough if you put them at a large enough redshift, so the frequency is right. Einstein telescope. Anyway, so there's a. I'm not sure I'm not sure there was this discussion at some point of building 4 LISAs. It was this Big Bang observatory, and I don't know to what extent anyone still seriously talks about it. But if you had a network of LISAs, you'd be able to do much better pointing. If you could do much better pointing, in principle, you might be able to just localize. If you do it well enough, so sub 1 degree, you'll be able to localize the galaxy from which the source came, and therefore just measuring. And therefore, since I identified the galaxy, you'd be able to really measure the redshift, and that would give you fantastic constraints. But I think the important thing is that H0 will essentially be the answer. We'll have an answer to H0 soon. This is, we'll see the extent to which that will still leave us with a controversy. There comes a point where, why would you want to measure some parameter even more precisely? What is the physics you might discover? But let me just, so half an hour left, so let me just switch tack a little bit and say put in the middle of the next decade and say, we have now measured H0 to be whatever it happens to be, and let's imagine it matches one of these. So if it doesn't match either, that's not great. There's a non-standard physics answer to that, but so let's say you confirm that you want to shout something, Ricardo? Sorry, I thought you wanted to. Let's say you see that the H0 that you measured is the Planck one. Okay, then the answer is very simple. Whatever happened in this calibration of Cepheids and building this distance ladder, something is very much off. Astrophysics, it's not a fundamental thing. But let's imagine that you actually confirm the result, right? So what can you possibly do in order to somehow make cosmology work? And the answer to that is, in fact, it's not very simple. One thing you can, so what are the possible solutions? And maybe I should put solutions in quotes because they're not very pretty. If it's really fundamental, right? If it's really true that there's a difference. One option for this, and again, somehow we're living in, it is in principle possible that we're living in some sort of void. So if this is somehow the average density in some local, averaged on some local distance, it's possible that we might be living in some sort of underdensity. And this might just give us the impression that things are receding. So really this whole local measurement of the supernova is really a result of just a change in this breaking of this homogeneous isotropic background. Now, this thing would have to be something of the order of 150 megaparsecs in size, and about 10% a 10% deviation from the average density. There's no way of getting anything like this out of theories of initial conditions. Okay, so it's just completely unknown how you would do this. So this is essentially this question that someone had about, what about the local peculiar velocities, etc. Doesn't that pollute this H0 measurement? And the answer is yes. In principle, you could have something kind of crazy, and then you just wouldn't know. So that's one. So that's a violation of cosmological principle. That's one thing that might be happening. The other one is, let's say, with more fundamental physics. So something might be off in the way that, remember that the way I was telling you about this is that you really are making two measurements. You're making measurements of distance without knowing what the scale is. So in the case of the CMB, you are putting in a sound horizon, right? And the sound horizon is intrinsically in all these angular diameter distance measurements. So the claim is that we know what the sound horizon is very well. From infinity to the sound horizon, some integral of the sound speed of radiation, which is roughly 1/3, some correction for baryons, and an h of z. So one way of fixing this H0 problem is exactly you want to have higher h today, so the way to achieve that is by making h higher also in the past, so you reduce the sound horizon. So roughly the statement is that you need to reduce the sound horizon from the 150 megaparsec, co-moving megaparsec, so where the BAO feature was, remember, that we think it has in lambda CDM, to something of the order 140. And that essentially solves this tension. So how might you be able to do that? So you just have to change the content of this integral somehow, right? So simplest thing to do is to just play around with h. Now, we're reasonably confident that since we got the CMB more or less correct, I mean, it's an amazing feat of science that we can predict that whole pattern of oscillations very well. So we don't really want to modify it over here, but at infinity, redshift infinity, we don't know anything. So maybe that's what you should do. But this wouldn't work because this integral really, h is very, very large in the far past, which means the contribution of very large redshifts to this integral is nothing. So the only way to really achieve anything is exactly to do something close to the redshift of recombination. So people have, let's see. Did I not write anything? Oh, no, here. So people have tried to play around with this. Let's say even the sort of vaguely standard physics might allow you to do something like that. So remember that h is squared, the Friedman equation is roughly rho radiation plus rho matter plus whatever. And this radiation is all the non-relativistic species, all the relativistic species. So this contains photons, but also contains neutrinos. Neutrinos we don't know very much about, so in principle maybe you can add an extra neutrino. And this would, the energy density, I was showing this yesterday, of any relativistic species is, provided that it's it's in some equilibrium state, is a temperature to the 4 times the Stefan-Boltzmann constant. and and there's some sort of g, which is the, so maybe actually that's not so. So okay, in dimensionless units look like this. Sorry, I'm confusing dimensions and not. So there's temperature to the 4, and g is a number which tells you about how many, about the spin of the objects, how many. If it's a fermion of spin half, it has 2 polarizations, and a photon has 2 also, etc. So it's the degeneracy here. In principle, I just might add another neutrino. So this, of course, increases the H. Changes over here. But turns out that, in fact, this doesn't really work very well, because these neutrinos, they're again some relativistic fluid. They have sound speed, right? They're relativistic. They have a sound speed 1/3. They also, it's called free stream. So when you kind of try to compress them, they try to get out from this local overdensity. And what that would do, since they're gravitating, these overdensities, neutrinos are gravitating, they would really begin to erase some of the structure of the CMB. So the higher order, the small scale oscillations would in fact be suppressed. And since we've measured them so well, there's not very much room for anything like this. So the parameter that people use to discuss this is N effective. So it's the number of relativistic degrees of freedom in addition to the photons that you have that enter the Friedmann equation. And the standard value for N effective is not quite 3. So there are 3 neutrinos in principle, but this is not quite 3, but it's 3.046. And the reason why it's not quite 3 is because the temperature of the neutrinos is firstly not exactly the same as at the photons, because they decoupled much earlier. But they were not completely decoupled during positron electron annihilation, and slightly the temperature was increased during that time. So this was sort of, people used to think it's just 3, that the temperature is some particular number that was predicted, when in fact this 0.46 appeared. People realized this was the case in the 90s, that there's this extra coefficient. So, but then you try to increase that a bit. So this is called dark radiation. And okay, it does exactly what you need to do. It increases your H, and therefore you become more compatible with Reese. So in this plot, this is the standard lambda CDM value. In principle, you can increase it a little bit. But as I said, you begin to erase structure. And since you're erasing structure at small scales, you're just not allowed to go as high in order to make this compatible with Reese. So if you want to fix it by fixing the sound horizon, you have to do it at recombination, and you have to do something smarter than just adding an extra relativistic particle. And sort of, they're not really any good ideas for what that might be. So that's one option. And the other option is the hockey stick. So you say, look, it's really just to do with what happens in the late universe. So somehow there's, this dark energy business we don't really understand so well. So maybe, let me just go back to this plot I had earlier. This one. So maybe at these very low redshifts, where we don't really have very good control of what's happening to expansion, at redshift of 0.2 or less, something kicks in to actually make H. It's a confusing plot because it's 1 plus Z. So make H not decrease quite as quickly as it would do. But in this case, it's sort of, it actually would look like it had to increase. But so you essentially want to accelerate the universe faster than the cosmological constant. And this would, so you change H0 locally, H0 at redshift less than whatever, 0.2, 0.3, something like that, by having W less than -1. Okay? And I will come back to this. But in the context of standard general relativity and something that looks like a standard perfect fluid, this is a catastrophically bad idea. So essentially, this is completely unstable. This does not. So people used to think it really doesn't. There's no theory which would do this at all. That's not quite true. But in order to do this, you have to really change the way that you describe in gravity. So this is catastrophically unstable in standard physics. Okay, And I'm going to do a computation which is a standard computation of inflationary cosmology, which sort of is useful for all sorts of purposes. But I will show this explicitly that essentially this is a disaster. But I think I'll start tomorrow. So, yeah, time for questions.